First of all, before we talk about this question, we should talk about what is meant by bond dissociation energy. That is the measure of the strength of a chemical bond. That means if a bond if the bond is higher in energy, that means higher energy to break that particular bond. That means it has higher dissociation energy. So now let's talk about these examples. First one has, all of them have halogens. The first one is, I'll draw only the halide and carbon bond. First one has iodine in it, and second one has bromine in it, and third one has similarly chlorine atom. And this chlorine, bromine, iodine, all are halogens. And if you can remember the periodic table, when you go down the group, the atomic size is getting bigger and bigger. All these halogens are group 7 atoms. So first one is fluorine, then chlorine, bromine, and then iodine. So when you go down the group, the atomic size, as I mentioned you earlier, it's going to be bigger. And when you consider the bond length in between this carbon, chlorine, carbon, bromine, and carbon iodine, the highest bond length should be possessed by this iodine. So when you consider the bond length, iodine carbon bond is very lengthy than that of bromine and carbon. And the lowest bond length should have by this carbon and chlorine. And when you consider the energy, this if the bond length is very high, that means the energetically it is very unstable. It is very easy to break this bond. So the bond dissociation energy will be very lower in those kind of bonds. So if you consider this carbon chlorine bond, as I told you earlier, it has very low bond length and thus very high strength in it. So that you need very high energy to break the carbon chlorine bond, and you need less energy to break this bromine carbon bond, since this bond is not that much strong than that of chlorine and carbon. Similarly, you need very low energy to break this iodine and carbon bond, because the bond strength of that is very lower than that of bromine or chlorine. So now you can think the bond dissociation, the energy that needs to break the bond is very high for this carbon and chlorine, and little lower to this bromine and carbon, and even less to this iodine and carbon. So the bond dissociation energy changes like this. So if you draw the three things again, since carbon and chlorine bond is very high in energy, you need very high energy to break that bond, and less energy to break bromine and carbon bond because it has less energy than that of carbon and chlorine. And you need even very low energy to break iodine and carbon because the bond strength is very much lower than other two. So this is the second one, is the how bond dissociation energy changes. And in the second one, it is about the bond again with the nitrogen atom. So if you draw these three molecules, first one has this kind of structure. So if you draw the structure, there should be only one single bond in between these two nitrogen atoms, and the second structure has double bond between these two nitrogen atoms, And third one is the normal nitrogen molecule. That means you should have triple bond, three bonds in between these two nitrogens. So as you all know, a single bond is lower in energy. It is not that stable than double bond. And you all know that triple bond is very high in, it's very stable. It is very hard to break that triple bond. And double bond, yes, you can break it, but it needs lower energy than triple bond, but higher energy than a single bond. So now it is very easy to figure out what has higher dissociation energy. If the bond strength is very high, that means you need that has very high dissociation energy. So since the triple bond is very high in, it's very strong, that means you need very high energy to break that. That means dissociation energy in that triple bond is very high. So it has the highest energy, dissociation energy, and the molecule with single bond in between two nitrogen atoms has lowest strength in it, in between that two nitrogen atoms, the bond I mean, and this bond dissociation energy is very low to that particular molecule. So this is how you figure out what molecule has the lowest or highest bond dissociation energy.